Welcome back to the Deep Dive. This is the place where we take the sources you send us and, well, we try to turn all that raw information into something you can actually use, structural knowledge.
And today we're really jumping in at the deep end.
Oh yeah, we are not just wading in the shallows of tech trends. We are going straight into the engineering bedrock of AI and machine learning.
That's right. Our mission today, it's really a first foray, a deep, but a very practical look into how AI and ML systems actually get built, deployed, and managed out there in the real world at scale.
So for you, our listener, the learner, we're sort of setting something aside here.
We are. We're skipping the heavy theoretical computer science. We're not going into the deep mathematics of, like, neural networks. We're focusing purely on the mechanics of implementation, the infrastructure choices you have to make, and I think this is critical, how you manage these incredibly complex systems to make sure they're compliant, stable, and can actually grow.
We're pulling back the curtain because I think when most people hear AI today, they're thinking about the final output, right?
Yours.
The chatbots, the image generators, the recommendation engines on their favorite shopping site.
But those outputs, they're just the tip of this massive, meticulously engineered iceberg.
And our goal today is to give you the language, the framework, to understand the structure of that whole iceberg underneath the water.
And to even start doing that, we have to draw what is probably the most crucial distinction in modern ML implementation. We call it the two paths of AI.
Okay.
And understanding this split, this fork in the road, it basically dictates every single infrastructure decision you're going to make from that point on.
So path one. This is the one most people are familiar with, even if they don't realize it. It's the most immediate. We're calling it the shortcut. Using AI.
Exactly. This is where you leverage these immensely powerful pre-trained models. These are systems that cost literally hundreds of millions of dollars and decades of research to build.
And they're just ready to go.
Instantly. Think about high accuracy vision recognition, or global language translation, or even highly specialized medical image analysis. You access these finished products through simple application programming interface calls, APIs. You are, in effect, a consumer of intelligence.
Okay, so that's path one, the consumer path. Path two sounds like the opposite. It's the advanced track, right? The deep end.
This is making AI. This is what you do when the problem you're facing is, proprietary, or it's just too unique for a standard tool.
So like you have your own financial data
or highly specific sensor readings from your factory floor, or confidential patient notes that you absolutely cannot upload to some public service.
I see.
In that case, you have to build, train, customize, and then manage a brand new model from scratch using your own private data.
And that's where the complexity just skyrockets.
It ramps up dramatically, yes.
Yeah.
But the level of control you get and the potential business value, it's exponentially higher.
Okay, these concepts are still a little abstract. I think to keep these two paths anchored in reality, we need a really solid analogy.
We absolutely do. It can be overwhelming without one, especially if this is your first real step into this domain.
All right, let's go back to our kitchen. We're trying to heat up some leftovers. That's our basic AI task, right?
Yeah.
Simple input. You want a desired output.
Perfect. So, path one, using AI.
That is reaching for the standard, off-the-shelf, incredibly powerful microwave.
The microwave. A finished product built by experts. It does what? 90% of common heating tasks. It does them instantly, reliably.
And you, the user, you don't care how it works. You don't care about the magnetron or the waveguides inside.
Yep.
You just put your standardized input in your plate of food, you press a button, and you get a result.
That is your pre-trained API. Instant utility, zero specialized engineering knowledge required on your part.
Okay, so that's the microwave. Then path two, making AI, is realizing that the microwave is not going to cut it.
Right. You don't need to heat leftovers. You need to create, say, perfectly stable industrial-grade pharmaceuticals.
Oh.
And they require extremely precise, continuous temperature control, humidity regulation, specialized air filtering, all inside a containment chamber. You need a specialized industrial oven.
And you can't just go buy that on Amazon.
Not at all. You can't just buy it. You have to design the entire thermal architecture. You have to source specialized heat-resistant materials. You have to set up redundant environmental controls, write the custom software to run it, and probably hire a team of engineers just to oversee its operation 204/7.
So it's infinitely more work, more complexity, more cost.
But the payoff is you achieve these hyper-specific, mission-critical results that no standard microwave could ever deliver.
So our deep dive today is really structured around knowing those professional trade-offs. When do you grab the microwave, the API, and when do you absolutely have to start the long journey of building that specialized industrial oven?
Exactly, and we'll start where most people should, with the shortcut, the AI microwave.
The beauty of that AI shortcut, I think, lies in abstraction. Like you said, we're talking about capabilities that, just a few years ago were cutting-edge data science research.
And now they're available instantly as a simple web service call.
So something like the Cloud Vision API.
Right, which can identify objects in a picture, recognize famous landmarks, read text with OCR, or even, detect faces and sentiment in images.
Or the Translation API.
Which handles dozens of languages just instantly. These services are built on these colossal data sets and years of optimization. You, the developer, you don't submit your data to some complex training environment.
You just send it to an API endpoint.
And you get a simple JSON response back in milliseconds. It's a fundamental shift.
That shift is radical.
Yeah.
It means the biggest hurdle in using this kind of sophisticated AI, it isn't the AI itself anymore.
No, not at all. It's the surrounding engineering. Specifically, how do you handle the data inputs and the outputs securely, and how do you do it at scale?
Okay, so let's tackle a classic problem there, a real implementation hurdle. Let's say we have an art gallery application.
Okay.
And it wants to use that Cloud Vision tech to recognize famous paintings from images that users upload.
And these users are external, right? They're museum visitors, maybe researchers. They shouldn't need a Google account or some special cloud identity to use the app.
Exactly. And here's the kicker, the constraint. We only want to allow the upload for a very limited temporary window, let's say 24 hours. We want to minimize our storage costs and our security liability.
This is a classic tension. Speed and accessibility on one side versus security and controlled access on the other.
Right, because if you just let anyone anonymously upload files to your cloud storage bucket where the files are kept, you're just inviting spam, abuse, maybe even compliance issues.
But if you try to manage user accounts and complex authentication for potentially millions of external users, the friction is just enormous. The whole project would grind to a halt.
So we're stuck. How do we solve this puzzle? We need temporary, secure, external access, but without all the heavy lifting of formal user authentication.
The robust, professional solution here is to implement a signed URL that expires after 24 hours.
Okay.
It elegantly addresses all three of those constraints: security, access, and the temporal limit, all at the same time.
Let's unpack that term, signed URL, because this is fundamental to secure cloud operations, not just for AI. When most people hear temporary access, I think they imagine a temporary password or a shared link they just hope nobody misuses.
Right.
Why is a signed URL so much better than that? A simpler, but much less secure approach.
Well, the difference really lies in the security principle itself. It's about proof of authorization. A generic password or a shared link that relies on secrecy.
If someone guesses the password, they're in.
They're in. A signed URL, on the other hand, relies on cryptography and, critically, on the principle of least privilege.
Least privilege, meaning the user only gets the exact permissions they need for that one task and absolutely nothing more.
Precisely. A signed URL is not a key to the entire kingdom. It is a very specific, time-limited token that you attach to a standard web URL, and that URL points directly to one specific resource.
In our case, the upload location in our cloud storage bucket.
Just that one spot. And the signed part is, as you can imagine, the entire security mechanism.
That's the cryptographic magic.
It is. The URL is cryptographically signed by your own server using a private key that's known only to your cloud project. And this signature, it essentially stamps the URL with three critical pieces of information.
Okay, what are they?
First, what resource it can access, just this one file upload location. Second, what permissions it grants. Upload or maybe read, but nothing else. No deleting, no listing other files.
And third, the time limit.
And when it expires, for example, 24 hours from the moment it was generated.
So walk me through it. The external user gets this long, complicated-looking signed URL. They use it to upload their painting image. What happens on the cloud server side when it receives that request?
So when the cloud storage service gets that request, it's not looking for a username and password. It's looking for that cryptographic signature embedded in the URL.
And it checks it?
It validates the signature against its own known public keys. If the signature is valid and the expiration time hasn't passed, The server knows unequivocally that this specific access request was pre-approved by a trusted source within your own project.
That distinction is paramount. That's huge. It means the security is actually built into the URL itself. It's proving the origin of the authorization. It's not relying on some separate external layer of user credentials.
Right.
It's like issuing a temporary, single-use, digitally verifiable ticket for a specific turnstile at a stadium.
That's a great analogy.
The ticket only works for that one turnstile, for that specific hour. And the turnstile itself validates the ticket's authenticity, not the user's personal ID.
And critically, once that 24-hour clock runs out, the signature becomes invalid, and that link just stops working instantly. It's self-managing security.
Which is so much better than trying to manage expiring passwords or generic access keys, which is just,
Yeah,
it's error-prone. It's a maintenance nightmare.
exactly. Signed URLs really encapsulate the best practice for this exact problem, giving temporary, secure, external access to data inputs.
So the core takeaway here is crystal clear. When you're using these powerful standardized AI capabilities and the pre-trained APIs are microwave, the complexity often shifts away from the AI algorithms themselves. It moves on to the secure, scalable mechanisms you need to handle the input data. And you've solved that security and access problem with some really elegant engineering long before the Vision API even processes the first pixel of that painting.
Okay, so we've established the security mechanism for the data input using signed URLs. That's solid. Now we have to transition from just securing the data to, well, housing the application itself.
Right. The code that generates the signed URL, that calls the Vision API, that manages the user sessions and displays the results, that all needs a home. We need infrastructure, a deployment strategy. And this step, I feel, is so fundamental, but it's often overlooked. It really dictates your ability to scale and how fast your developers can move.
It absolutely does. Where the application lives, that deployment choice, it determines how easily you can go from 10 users to 10 million. It determines how resilient your system is to failure and, crucially, how much time your developers spend writing business logic versus just managing servers.
All right, let's dive into another demanding scenario. A huge global e-commerce company is building a new feature.
Okay.
They need to handle millions of concurrent, globally distributed users who are uploading and sharing pictures. This demands instant global scale.
A very common requirement these days.
But the biggest priority for the internal development team is this. They must focus purely on writing the application code, the business logic. That's it. No provisioning servers, no managing operating systems, no patching, no manual scaling, zero infrastructure work.
Okay, when that constraint, that developers must be shielded entirely from infrastructure management, when that is the #1 priority, the solution has to be a fully managed platform.
It has to be.
You have to use a deployment model that just handles everything beneath the code layer automatically. And for this specific set of requirements, the correct choice is App Engine.
App Engine, which is known as a platform as a service or PaaS.
Yeah.
So explain why this architectural choice is such a perfect fit for that goal of letting developers focus only on code, especially in a high-scale global context.
Well, App Engine provides a complete managed ecosystem. You just give it your compiled code, whether that's Python, Go, Node.js, Java, whatever, and App Engine just takes over.
It handles everything else.
Everything. It manages the operating system, the networking, the patching of security vulnerabilities, the load balancing, the entire deployment environment, and most importantly, for a scenario with millions of global users, it handles the auto-scaling.
So App Engine is essentially saying, give us the recipe, your code, and we will take care of the entire kitchen, the infrastructure completely.
That's a perfect way to put it. If your traffic suddenly spikes globally, App Engine automatically provisions and deploys new instances of your application across different regions to handle that load. It ensures low latency for users everywhere.
And the flip side.
If traffic drops off overnight, it scales those instances right back down to save you money. This level of automated management is crucial because it ensures the developers never have to stop coding features to become systems administrators who are manually fiddling with servers or load balancers.
Okay, now this is where we need to introduce some friction, because there are other powerful options out there. Why don't we just use raw virtual machines, VMs, on something like Compute Engine? That gives us ultimate control.
A fair question.
Or even better, why not use Google Kubernetes Engine, GKE? That's often seen as the modern standard for microservices and cloud-native apps.
That's a critical distinction to make, and it's a conversation every engineering team has. Let's use our appliance analogy again to categorize these three main deployment models.
Okay, lay them out for us.
All right. Compute engine, which is raw VMs, is infrastructure as a service, or IaaS. This is like buying the raw materials. You're buying the steel, the heating coils, the insulation to build your specialized oven completely from
So
scratch.
you have 100% control.
Total control over the operating system, the drivers, every single configuration parameter. But that also means you are responsible for everything: provisioning, patching, security, monitoring, manually coding your own scaling groups. This fundamentally violates that core requirement that developers focus purely on code.
Right. Extreme control, but also maximum management overhead.
Yeah.
Not what they wanted.
Then you have Google Kubernetes Engine, GKE. This is often called container as a service or a managed orchestration layer. This is like buying a self-assembled gourmet kitchen kit.
I like that.
You get prefab cabinets, high-end appliances, great blueprints. It's incredibly powerful, flexible, essential for complex microservices. However, you are still responsible for managing the cluster itself.
So what does that mean in practice?
It means you're still patching the Kubernetes control plane nodes, you're managing the cluster's network policies, you're defining the specific auto-scaling rules for the cluster's resources. It removes some of the operational burden compared to raw VMs for sure, but it still requires significant infrastructure expertise and ongoing maintenance.
So with GKE, developers still have to understand container orchestration and cluster health, which again isn't a pure focus on the code.
Correct. Which brings us to the third option, App Engine, the POS model. This is the fully managed, pre-built appliance. You just plug it in, and it handles everything behind the scenes. Developers upload their app, and they stop worrying about the environment it runs in.
And because the company's main objective was that absolute zero infrastructure overhead for the development team, facing this massive, unpredictable global scale.
App Engine is the clear professional winner. It's a perfect example of matching the technology choice to the specific business and engineering priority.
It's the highest level of abstraction, and it respects the developer's time and talent by just removing all those other distractions. It's so important to remember that the most powerful tool, like GKE, isn't always the right tool if it contradicts your primary management goal.
Exactly. Use the simplest tool that perfectly meets the scale and the management constraints you're working with.
So we've successfully covered the AI shortcut, the microwave, and the managed structure where that consumer application lives on App Engine. Now we have to enter the territory of the specialized industrial oven.
Now we're making AI.
This is when those pre-trained APIs just aren't enough. Maybe you're dealing with proprietary data or a really specific regulatory requirement, or a truly unique prediction problem, like a custom healthcare risk model.
Right. And when you start building and managing custom models at a professional scale, you are moving into the discipline of MLOps, machine learning operations.
And that requires a dedicated, unified platform to manage the entire ML lifecycle, from data prep to training to deployment, and critically, to monitoring what happens after deployment.
And this unified professional suite is what platforms like Vertex AI are built to provide.
Okay, so let's start at the beginning of that custom model journey, the training phase. This requires, astronomical amounts of compute power. We're talking huge clusters of specialized hardware like GPUs or TPUs.
And these training jobs can last for days, sometimes weeks.
So the challenge we face is an operational one. A data science team wants to train a cutting-edge custom neural network using a popular framework, say TensorFlow or PyTorch.
But, and this is the same theme, they refuse to manually provision, configure, and manage all the training servers. They're data scientists, not cluster operators. They want to focus on the model, not the infrastructure.
Because manually provisioning a multi-GPU cluster is notoriously complex. You have to get all the driver compatibilities right, manage the underlying OS, establish fault tolerance, set up all the networking for distributed training jobs.
And if the job fails halfway through, you're stuck manually restarting it, making sure checkpoints were saved properly. It's a huge headache.
The solution here, then, has to be a managed service.
It is. It's Vertex AI Training. This is a managed service designed specifically to accept your training code, your configuration requirements. I need 4 NVIDIA A100 GPUs, and it just executes it on automatically provisioned infrastructure. You submit the job definition, and the platform handles all that complexity for you.
So instead of managing the raw VMs, we're now just managing the job itself. How does Vertex AI Training handle all that heavy lifting that a manual compute engine setup would force on you?
It manages the entire cluster lifecycle automatically. When you submit the job, it provisions the required compute cluster, it installs the necessary libraries and drivers, copies the data over, initiates the training run, and manages the distribution of the workload across all the different nodes.
What about failures?
If a node fails, it attempts to recover.
Yeah.
And crucially, once the model is trained and the artifacts are saved, the entire infrastructure is automatically torn down.
So you only pay for what you use.
You only pay for the compute time used during that training run, not for a bunch of idle servers sitting around.
That is the efficiency gain for an ML engineer. Their focus shifts away from the headaches of provisioning Linux and GPU drivers and moves to the high-value tasks.
Exactly. Hyperparameter tuning, feature engineering, evaluating model architecture, it speeds up the iteration cycle dramatically.
Okay, so we've trained the model. But once we move into custom models, especially for regulated industries, finance, healthcare, insurance, the responsibility level just changes completely.
It's a whole new ballgame. It's no longer just about optimizing for accuracy. It's about compliance, auditability, and regulatory adherence. The models simply cannot be black boxes.
Because if the model makes a decision that really impacts someone's life, like denying a loan or suggesting a medical treatment, regulators and internal compliance teams demand transparency.
They have to.
Let's stick with that loan approval model scenario. A customer gets rejected. Financial regulations, like fair lending practices, mandate that the bank has to provide a legally sound, specific reason for that rejection. The model can't just spit out rejected.
That black box rejection is a massive compliance risk. So the solution is to enable Vertex Explainable AI, and specifically to use its feature attributions capabilities when you're making a prediction.
Okay, explain feature attributions simply. Is this just the model guessing which variable was the most important?
No, it's not a guess at all. It's a rigorous mathematical calculation. Feature attributions determine the exact percentage-based contribution of each input variable or feature to that one specific prediction outcome.
For that one customer.
For that one customer. So if your model uses 50 different inputs, Explainable AI will mathematically isolate which features move the needle toward accept and which ones moved it toward reject.
So if a customer's debt-to-income ratio is high and their credit history is short, what does the attribution look like?
It means you can generate an output that literally says the debt-to-income ratio contributed 40% to the negative outcome and the length of credit history contributed 35%. The other 25% might be spread across other minor factors.
And the key here is that this attribution is local, right? It only applies to this one specific customer's prediction.
Exactly. It's not a general statement about the model as a whole.
And that's the difference between a global explanation, like the model cares about debt, and a local one. Your high debt was the specific reason for your rejection.
And that local, specific audit trail is precisely what the compliance team needs to satisfy the regulators. It turns the opaque model into an auditable, transparent process.
So the takeaway is, if you are building models that impact human livelihood in any way,
you have to turn on Explainable AI. It's fundamental. It shifts the burden of proof from just trust us, the model is good, to here's the mathematically derived contribution of every single factor that led to this decision.
Okay, so that's transparency. But compliance often dictates not just how decisions are made, but where the data physically resides and where the processing happens.
This is the concept of data residency, and in certain geopolitical or industry contexts, it is the strictest mandate of all.
Our next scenario highlights this perfectly. We have a major healthcare provider in the Middle East. They're operating under very strict regional data laws in places like Dubai or Doha.
Okay.
They need to summarize confidential patient notes using advanced models like large language models. But the regulation mandates that this sensitive patient data must never leave that specific geographic region. It cannot cross international borders, even virtually.
And if that data leaks or gets processed outside the approved territory, you're talking about huge regulatory violations, massive fines, and a complete loss of public trust.
So how do we ensure with technical certainty that this data residency requirement is met?
This is a textbook example of needing a belt and suspenders approach. You can't just rely on a single configuration. It's too risky. You need layers of technical enforcement.
To lay out the two essential technical components that deliver that certainty.
First, you absolutely must use a regional API endpoint. Instead of connecting to the default global endpoint, which might route your traffic anywhere for efficiency, you have to explicitly configure your application to use the regional one.
So something like me-central1-AI platform.googlelepus.com.
Exactly. That ensures that the model processing and the compute resources being used are physically located within that defined Middle East region.
Okay, that addresses the intent. It directs the traffic to the right physical place. But what about mistakes? What if a developer makes a coding error and accidentally routes data to a global endpoint, or tries to transfer the summarized results to a global storage bucket? We need an ultimate failsafe.
And that's where the second, absolutely critical layer comes in, enclosing the entire project within a VPC service control perimeter.
Okay, that terminology, VPC Service Control, sounds extremely technical. Can you simplify that mechanism for us?
I can try. Think of the regional API endpoint as telling your data truck go only to the Middle East warehouse. VPC service control is the physical, unbreachable perimeter wall around that warehouse and everything inside it. Your cloud storage buckets, your BigQuery tables, your Vertex AI models, everything.
So it's like a digital fence.
It's more than a fence. It's an absolute wall that prevents any sensitive data from leaving that approved zone. The perimeter strictly defines the boundaries for data movement.
So if an engineer accidentally writes some code that tries to move data to a storage bucket in, say, Europe,
The VPC service control perimeter will block that egress attempt. It doesn't matter if the engineer has the necessary authorization credentials. It treats that egress attempt as a violation of the security perimeter and denies the request on the spot.
I see. So the combination is what makes it so powerful.
Mhm.
The regional API endpoint guarantees the processing is done in the right region.
And the VPC service control perimeter guarantees, as a mandatory control layer, that the data cannot leak or be transferred outside that approved region under any circumstances.
That layered enforcement is how professional organizations achieve that strict regulatory compliance for data residency. All right, so we've achieved compliance, we've deployed our custom model securely, it's live. It's approving loans, summarizing patient notes. Now we have to confront the single biggest, most inevitable enemy of every deployed ML model,
Time and chain.
the inevitable problem of data drift.
It sounds subtle, but it is the silent killer of model quality. Data drift just means that the statistics and the distribution of the production data your model sees, now today's input features, have changed compared to the static training data the model learned from 6 months ago.
And why is this inevitable?
Because the world is dynamic. I mean, if your model predicts stock movements, the global economic landscape changes. If your model predicts clothing sales, fashion trends shift, unexpected weather events happen.
Or in our loan model example, if it was trained before recession and then suddenly it's seeing data during a recession, the whole relationship between the features and the outcomes has fundamentally changed.
Exactly. The model becomes increasingly inaccurate because it's operating on an outdated view of reality.
And because these changes are often subtle and gradual, nobody might even notice the performance degrading until it's too late, and the business outcomes are already suffering. You can't have someone manually checking data distributions every day across hundreds of models.
You need automated vigilance. So the professional solution for this kind of anticipatory maintenance is to use Vertex AI Model Monitoring and to explicitly track the prediction drift metric.
Okay, how exactly does model monitoring detect this, and what's the difference between tracking prediction drift and just tracking the model's overall accuracy score?
Well, tracking accuracy requires you to wait for the true labels. You have to wait to see, did the customer actually default on the loan?
Which could take 6 months, a year.
Right, it's a lagging indicator. Tracking prediction drift is proactive. Vertex AI Model Monitoring constantly analyzes the incoming stream of production data. It uses statistical methods to compare the distribution of the incoming feature values, the input data against the established baseline characteristics of the original training data.
So if our training data showed that 90% of loan applicants had a steady employment history, and suddenly the live production data shows only 60% have that, maybe because of an economic contraction.
That's a huge drift. The system flags that deviation immediately, and it calculates a prediction drift metric score.
And when that score crosses a certain line,
When it exceeds a statistically defined threshold, it automatically triggers an alert. And this happens even before you know for sure if the model's accuracy has actually fallen. It's detecting the cause of the inevitable accuracy drop, the change in the data inputs, and it's signaling that retraining or some kind of intervention is required.
that is such a critical distinction for our learner. We're moving from reactive maintenance, waiting for the model to fail, to proactive, anticipatory MLOs, detecting the structural shift in the data environment that will cause the model to fail. Okay, last piece of the puzzle. Models aren't deployed and then just forgotten. If we're going to all the trouble of building a custom system, we expect it to get better over time.
Of course.
So a live model, like a web service offering personalized product recommendations, it needs to learn from its recent successes and failures.
Absolutely. No matter how perfectly you trained that initial model, it only reflects the historical data it saw. To stay relevant and improve, the model has to be continuously enriched by real-world interaction data. This means you have to build a structured feedback loop.
So what's the specific action our e-commerce company needs to take to make sure the recommendation model improves? It has to be something that feeds results back into the training data set, right?
Right. The essential action is to save a comprehensive history of the recommendations made and the corresponding user feedback and results into a scalable, accessible system like BigQuery, so it can be used as future training data.
Okay, let's define the elements of that loop. The model outputs a recommendation. That's the action. What happens next is the crucial piece of data we need to capture.
The user then provides feedback. They might click the recommended item, add it to their cart, buy it, or they might just ignore it completely. This raw interaction data is a treasure trove.
So if the user buys the recommended product, the model was right. That's positive feedback.
And if they buy something else entirely, the model was wrong. That's negative feedback.
And we have to log all this. The input features like the user's profile and the time of day, the specific recommendation output, and then that feedback, the click, the ignore, the purchase, and store it all somewhere that can handle the scale. Why BigQuery specifically for this?
BigQuery is designed for exactly this. Massive scale, high-velocity analytical data storage. This interaction history can quickly grow to petabytes of data, and BigQuery is optimized for running the complex queries and aggregations that data scientists need to prepare the next training data set.
So all this new data is time-stamped, it's clean.
It's the perfect material for the next iteration of the model. This collection of new labeled real-world interactions, what we call the feedback data, it becomes the enriched training material. The model learns what recommendations were actually acted upon in the current market environment.
And that formalized continuous feedback loop is really the essence of MLOps maturity, isn't it? The next version of the model isn't based on some aging snapshot of history.
It incorporates the very latest shifts in customer preferences, product catalog changes, and user behavior. Without that structured approach, even the most powerful models will just degrade into irrelevance over time.
So it's a cycle. Deploy, observe, collect feedback, retrain. That mechanism defines a healthy, continuously improving ML system operating out there in the deep end of customized intelligence.
Wow.
That was a really comprehensive deep dive into the engineering reality of AI implementation and management. We started with the fastest shortcut, and we trapped the journey all the way into these highly regulated, continuously improving custom model pipelines.
And the key takeaway, the thing we really hope sticks with you, the learner, is the importance of choosing the right tool for the job. It's not about always picking the most powerful thing.
Right. You use the pre-trained APIs and the managed services like Cloud Vision or App Engine, the microwave approach, when you need immediate speed, simplicity, and massive scale for standardized, non-proprietary tasks.
And you reserve the specialized industrial oven, the platform tools like Vertex AI Training, Explainable AI, Model Monitoring, and the rigorous security of VPC Service Control for when your needs demand ultimate control, customization, and adherence to those strict regulatory mandates, like data residency.
And of course, for that continuous, data-driven performance improvement.
We saw how modern platforms are just designed specifically to handle these inherent complexities, guaranteeing secure, temporary data access with cryptographic signed URLs.
Ensuring developer velocity and scale with the PANAS architecture of App Engine.
And critically, maintaining compliance through that belt and suspenders approach of regional API endpoints, coupled with VPC service control perimeters for absolute data residency, and of course, transparency through feature attributions.
All of these tools allow engineers to focus on the intelligence outcome, not the operational overhead of the underlying servers. I think success in AI implementation today is less about inventing a brand new algorithm.
And much more about brilliantly stitching together these specialized managed components.
So finally, let's leave you with that provocative thought that brings us right back to the most challenging problem we discussed.
Data drift.
We established that data drift is this inevitable divergence between the clean training data and the messy, ever-changing real world, and that it leads to degraded performance. Given that need for constant monitoring, we want you to consider this. What kind of unexpected real-world event, economic, social, or environmental, do you think would cause the most rapid and severe prediction drift in a major AI system that relies on highly stable human behavior. Something like a system predicting traffic flows or predicting peak electricity demand.
Yeah, think about a shock that instantly changes consumer patterns or commuting habits, or even just the underlying infrastructure utilization across an entire continent. That kind of sudden, profound societal shift would render decades of historical training data almost irrelevant overnight.
Something to ponder as you look at the world around you, because the performance of an AI model is, in many ways, a direct, if sometimes delayed, mirror of the unpredictable environment it operates in.
Thank you for joining us for this deep dive into the foundations of practical AI management and implementation.
We'll catch you next time.